Thank you very much. Hello, everyone. My name is Pierre Palud. As Javier said, I'm now a doctor. I've defended my thesis in December. So I'm glad to tell you today about some of the work that I've led during these 3 years. Part of it was led in collaboration with Lucas. And I had two PhD directors. One was Franck Le Petit, sitting in this very room, and so an astronomer. And the other one, Pierre Chenet, is a statistician. So I have more of a statistical background, and my PhD was to work at the interface of the two fields. The origin of my PhD was really the rise of new images, such as the Orion B maps that a few people already described today. So the point of this kind of my studies is that this kind of map is to be more and more current, more and more common in the years to come. For instance, with the rise of the James Webb Spatial Telescope that provides huge maps with hundreds of thousands or millions of pixels with good spectral resolutions, depending on the telescope. And the question that I'm going to tackle in this presentation is how to exploit these kind of very rich maps, in particular, in order to infer physical conditions in the observed environments. So these days, the observations tend to be large hyperspectral cubes. We have many pixels, we have many spectral channels, and these environments that are observed require advanced astrochemical models in order to be understood. So for instance, the Meudon PDR code for PDRs, the Paris-Durham model for shock models, etc. Another aspect that has not been really mentioned today is the fact that observations nowadays, they have complex, the uncertainties on the observations might be complex. So that's something that I will talk about a bit. So that's one side, the observations, but how, if we want to infer physical parameter, physical conditions from the observations, we need physical models. And these physical models were, so part of it was presented in previous presentation, but nowadays these physical models tend to be more and more complex, including each day more microprocesses, and tend to become computationally more intensive. So usually these the comparison between the bridge between observations and models is done this way. So first, the slow and complex models are tackled by a grid of interpolations. The comparison between observations and models is used using a Gaussian noise. The physical information a priori is encoded in validity intervals on the physical conditions. And the estimation itself is performed using a least square minimization, which leads to no uncertainty quantification on the inference results. And this is problematic. This is not satisfying for the maps that we have today. And this is an example why. On the left, you can see an observation from the Spitzer telescope of the Carina Nebula, a nebula in the galaxy. And in the middle, what you can see is for one pixel, in purple are the observations with the associated error bars. And in green, you have the reproduced observations made by the fitted physical parameters. So this is fine. The green curve matches perfectly the purple one. So one would think that the estimation is satisfying. But if we look at the map of reconstructed thermal pressure, for instance, we see that the map is really physically not meaningful. It shows some brutal transitions that are obviously not physical. This patchwork, these brutal transitions come from the fact that this estimation was performed using least square minimization using a pixel-wise approach. And since the approach performed here was based on optimization, there is no estimation associated for the uncertainties. So really what we have resulting from this analysis is this map, and this does not permit to do physical analysis of the Carina Nebula. So what I did during my PhD was first to accelerate, like Luca explained, the approximation of the complex of the complex numerical models of the interstellar medium. And then a few aspects. The comparison between the observation model was improved through a thorough noise modeling. Then the physical information a priori was improved using a spatial regularization in order to obtain smooth maps, as one would expect in reality. And the estimation of physical conditions was not anymore performed using an optimization approach, but a Bayesian inference, which provides uncertainty quantification associated with the estimates. So I will not talk about the Bayesian methodology. I think today the most interesting aspects are the noise modeling and the spatial regularization, but just a quick word about how it works. In optimization, which is most common approach, I guess, you would have something that Luca called a loss function, which is the function that you try to minimize. And this function is divided in general in two components, one data fidelity term that encodes the observation model, the noise model, so generally least square, for instance. And you would have a regularization function that encodes the prior knowledge. So here, for instance, on the right, you would have an example of such loss function with multiple local minima and stuff. And you want to find the minimum. With the Bayesian inference approach, you define a posterior posterior distribution, which is comparable to the loss function, except that instead of having a function to minimize, you now have a distribution to sample, and from which you want to extract information such as credibility intervals and the mean. So for instance, here you start with the posterior distribution, which is defined with a likelihood function and a prior distribution, both equivalent to their analogous to optimization framework. From this posterior distribution, you draw samples using, for instance, an NCMC algorithm, Monte Carlo Markov chain. And then you evaluate Monte Carlo estimators from the samples. So the mean, for instance, the credibility intervals. This is technical, just to say that we don't do optimization, but we use a analogous yet different approach. So as I said, two things that are very important, the likelihood function that encodes the noise model and the physical information a priori encoded in the spatial regularization. So I'm going to talk about both a bit more. First, the observation model that we use is a bit complicated. So usually, as I said, we use Gaussian noise model, so least square minimization. In our case, we use something a bit more advanced, a bit more sophisticated. So we have an additive noise, again, Gaussian, as we can expect, as we already use. And we add to this noise model a multiplicative log normal noise that encodes calibration error or model misspecification. Model misspecification, it's just, okay, I have the Meudon PDR code. How well do I think that it's going to emulate the clouds that I'm going to observe? The problem with this noise model is that the associated likelihood function does not have a closed form. So this is a problem for statisticians, but this is a problem in general when one wants to perform inference or to write the problem. So usually in astrophysics, but more generally in statistics, people tend to resort to a Gaussian approximation, in other words, to neglect the multiplicative noise. In our case, since the variance of the multiplicative noise is quite high, this is not something we can do, or to use a Gaussian approximation of the multiplicative noise instead of a log norm. So the problem with that is that it works in small variances, but it doesn't for large variances. What I'm showing here is in blue, the probability density function of a multiplicative noise, and in orange, the probability density function of the Gaussian approximation. And you can see that it works fine on the left, but we are using a large variance multiplicative noise. So we are in this case, and in this case, to use a Gaussian approximation does not work, doesn't attend our needs. So we needed to we proposed something new in our paper from 2023. We noticed that there are two extreme cases, basically. The first case is either we are in high SNR regime, in which case the additive noise here can be neglected in front to this component here. in which case the multiplicative noise dominates. And so we use basically a log normal approximation. The other case, on the other hand, if this is extremely low, meaning if we are in the low SNR regime, then one can neglect this part and the observation is mainly deteriorated by additive noise. So we use a Gaussian additive approximation and we use a weighted geometry mean in order to make a smooth transition between the two. Just this is a bit technical, but the takeaway message is that we can model this complicated observation model and handle it in an inference procedure. And regarding the prior distribution, the physical information that we are going to use, we favor smooth maps. So I'm not going to give the mathematical details, but this is basically what we could get without spatial regularization. So again, very some unsmooth variations. And here we get the same results, but with the spatial regularization. And in this kind of map, we can identify better the different regions of the cloud that we are analyzing. For instance, here in the Carina Nebula, we know that there are the cloud appears in different planes. So here on the foreground and here in the background. So we can see it again in this map while we can't in this one.
2 minutes.
Hey, was a bit ambitious. So just to illustrate a bit the capabilities of the inference model and of the overall technique that I presented. So I generated maps of a fictitious molecular cloud, and from these true maps, I generated using the Meudon PDR code and the noise model that I presented some fictitious observed maps of 12 CO. And the goal was from these maps of 12 CO to reconstruct these true maps of physical parameters. So this is what we get if we use the classical method with with optimization and without spatial regularization. So these are just reconstructing SNR, the higher the better. So with the classical method, the results are really unsatisfying, but with our methods, we get smooth maps with credibility intervals. And very quickly, so Jan talked earlier about the cool big brother of Orion B, Orion A. We applied our methods to the OMC1 cloud, that is a molecular cloud from Orion A. These are the 4 lines that we use for our inversion. So CH+, 2 lines of 12 CO and 1 line of HCO+. This is the result with the classic method that doesn't take into account Bayesian inversion, Bayesian method and spatial regularization. These are our results where we can identify the different regions. For instance, the Orion bar here, the Orion South region here, and credibility intervals. In conclusion, what I've presented to you today are mostly on the modeling aspects, the fact that using the Meudon PDR code fast emulator, we could perform complex inference. We use the realistic observation model and physically meaningful spatial regularization. And I've shown 2 applications, one on a large synthetic realistic case and one on the OMC1 large map. I would like to put the emphasis on the fact that the method that I've shown you is very general. It's not specific to the Meudon PDR code. It's not specific to photodissociation regions, and it's not even specific to the interstellar medium. And finally, the code that I used derived for my inversions can be found online, either on GitHub, IP, or read the docs, and something for again, for the neural networks that we derived with Luca using PyTorch. Thank you for your attention.
Yeah.
Yes, I didn't get the core message. In principle, you say that the pixelwise approach is trying to repeat your data is not necessarily good one. But smoothing data, in principle, I don't need the pixels anymore as I was having them initially at the very beginning. I'm just removing information with your approach. In principle, there is information in these pixels which is fundamental and which would help us to understand better the physics. So you are sort of smoothing out, information which to me seems to be essential.
Thing is, I agree with you. If I was smoothing, if I was reducing the size of the number of pixels doing stacking, then I would be losing information. But there, I'm just telling my map inversions that my inversion method that one pixel should not be too far from the other one. It's not exactly smoothing the results. It's just saying that, okay, if I have a diffuse cloud, for instance, where I know that the SNR might be low, but I know that the environment covers a large region, then I should have similar values for neighboring pixels. So,
but in principle, you don't know. So you're assuming.
No, I'm not. I mean, you are at the core of the what I want to say, and thank you for your question. This is not smoothing, because smoothing would be indeed blind, because it would treat all pixels similarly. Here, when you are doing Bayesian inversion, the spatial regularization is just is put in comparison with data. It's just this. Sorry, these two equations. If you are absolutely sure about the Aurora construction, there's only one specific values that explain your pixels, then the likelihood will overweight your spatial regularization. It will drive the posterior distribution. On the contrary, and so in high SNR regions, the data fidelity term will drive the posterior distribution. This spatial regularization term, it's mainly relevant for low SNR regions that tend to be wide. Was that clearer?
It helped.
Thank you. Jan?
Yeah, I had a similar question actually. So you explained very well how the spatial regularization here happens during the Bayesian inference and not as a posterior post-treatment of the results. So it's indeed not a smoothing. But there's one thing which I'm always worried about is the fact that this thing is isotropic in the way it treats its surroundings. So yes, you can have to the left a pixel which is very well determined, to the right one which isn't, and then that creates the anisotropy. But I don't know to what extent, because actually the two physical examples that you showed us, both Carina and Oran A, they have edges. They have very prominent edges which completely disappear when after the. So I'm thinking more in because that's more my background in terms of image processing and stuff like diffusion to remove noise. So isotropic diffusion is just Gaussian smoothing, and then you lose information. There is anisotropic diffusion, which smoothes things in direction where there isn't much variation, but is able to retain edges, even sharp ones, where there are edges. So I have no idea how that translates to the spatial regularization term in the Bayesian inference. But is that something like that relevant, and is that possible to implement?
Yes.
To retain sharp edges where they are sharp edges.
There are a few ways. Thank you for first. It's a very good question. It's indeed you have a whole family of spatial regularization functions, and the one I've chosen is indeed based on Gaussian and would tend to blur clear fractures. I don't know how to say that. Clear transitions. Thing is, in a quick response for this case, we don't see in Orion A or MC1, we don't see clear transitions, clear fractures in the observation. So a priori, we would be surprised to see any in the inference results. So that's first thing. Second thing, so as I said, you have a whole family of spatial regularization functions. And the one I've used is a specific example, but you have some that indeed preserve edges like that. Total variation is one example, but it's not the one I've indeed implemented. Depending on the cloud that you are observing, the prior information that you're going to use is obviously gonna change. It would be possible in the code that I've published, but it's not something that I personally implemented. But if you already know where the clear transition is, you could do it manually in the way I've implemented stuff, but maybe this is a detail.